revisiting the question that Manojit, you asked last time about whether it's enough to have only the 1s orbitals on the 2 hydrogen atoms, for example, when we are doing a calculation for each 2 molecule. So I gave a long answer. Let me give you a shorter answer today, which is sort of more relevant to our discussion on tight binding model in this course, which is that that's the starting point. And so if you include more orbitals, your sort of basis gets larger. So in that sense, you have more freedom to express the correct forms of the wave functions in the molecule. But the 2 1s orbitals on the 2 hydrogen atoms are just the bare minimum that you need. So if you think of any other molecule or solid for that matter, the orbitals that are occupied, particularly we are talking of the valence orbitals, which are responsible for bonding. So those orbitals must be included in your calculation, obviously, because otherwise you won't be able to describe the electrons properly. But if you include more, your freedom of expressing the wave functions in your system, molecular or solid, increases. Okay. So we were discussing the tight binding model.
Sir?
Yes.
Sir, please switch off the video of the.
This one?
Yes, sir.
So we were discussing tight binding model, and the general idea, as I said here, was using the atomic orbitals as the basis functions for representing the electronic wave functions in a molecule or solid. So we started with a simple diatomic molecule, and there was some small mistake here. So one of these has to be 1 plus minus alpha p, the other has to be minus plus. So please correct that. So this is for a diatomic molecule. So let me go over these terms once again, and then we'll go over to the solids today. So this H11, H12, these are matrix elements of the Hamiltonian. And I repeat, the Hamiltonian of the system that we are interested in. It could be a molecule. In this case, it's a molecule. It could be a solid. So it's the full Hamiltonian of the solid or the molecule. I'll write that in more explicitly later on. So it's the matrix element of that Hamiltonian in the basis of the atomic wave functions. So these wave functions, phi A, phi B. Phi A is a wave function on an atom which is, let's say, located at Ri. This one is an atomic wave function located on an atom at Rj. So in principle, I can have more than 1 atomic orbitals on each atom. So if I have, let's say, n atoms in the system, and the ith atom has, how do I write it? Ni orbitals on it that I include in my basis, then the total number of orbitals, total number of such basis functions I'll have is Ni orbitals on the ith atom. So sum over I going from 1 to capital N. So that will be the total number of orbitals in my basis, total number of basis functions. And if I want to write it in a matrix form, it will be this times this cross this matrix. And then, so these H11, H22, these are matrix elements So here we are taking a simple case where there is only two atoms and there is only one orbital in each atom. So I need to worry about only two orbitals. And the matrix element of the Hamiltonian in the first orbital is written as H11. On the second orbital, it's H22. And I'll have cross terms, the off-diagonal matrix elements, H12. So, so if my atoms are different, let's say if I have a molecule, something like lithium hydride, then I'll take the 1s orbital on the hydrogen atom, 2s orbital on the lithium atom. So these two are different, the atoms are different, orbitals are different. So H11 and H22 would be different. So in this case, this will be a non-zero number, and it will depend, basically it would ultimately depend on the electronegativity difference of the two atoms, and that's called whether you have a polarity on the bond or not. And when you solve this problem, you get these two values for that coefficients, for these two coefficients. And one gives you the bonding state, the other gives you the anti-bonding state that you have sort of learned in your, I don't know, basic chemistry course, or you could be doing it in your molecular physics course. And alpha can be expressed in terms of this quantity delta epsilon. And when delta epsilon is 0, that is when the two atoms are identical, then of course this will be 0. And so you have C1, C2 equal to 1 over root 2 in one case, and in another case you have one as 1 over root 2, the other as minus 1 over root 2. So that those two will give you the bonding and the anti-bonding states. And these off-diagonal matrix elements, H12, these are sometimes in the molecular context, these are called covalent terms or covalent energy. And in the context of solids, these are called the hopping integrals. So it connects orbital on one atom to the orbital on another atom. Okay. So that is about the molecules. So let us now take up the situation of solids. So let us fix the notation first. So we have a crystalline solid, so that the potential U of R is lattice periodic. Since we are neglecting electron-electron interactions, this U comes entirely from the interaction of the electrons with the positively charged ions. And in what I'll do, in general, we'll assume that we can have more than one atoms at each lattice site, at each lattice point, in the sense that I can have more than one atom basis. So it's a general formalism. So R, these capital R, these vectors represent the lattice vectors. So these are these mathematical objects, the lattice vectors. And given a lattice vector, the atom positions are given by, so given a lattice vector Ri or R, let us say, the atom positions are given by quantities like this. So these are atom positions. Just to give you a simple example to illustrate what we are talking about. So for example, if I take this hexagonal lattice, the honeycomb lattice that we discussed, and which I said cannot be described by a single atom basis. So you need to include something like this. So to include this, so then these two atoms are needed to describe such a lattice. So then this could be my lattice vector. This position could be my lattice vector R. And then there will be two di's corresponding to. So whatever my origin is, this could be my lattice vector R. And the two atoms would then be sitting at one at the vector as 0. And the D2 would be the vector from here to here. So this could be my D2. So given a particular R plus D1 and R plus G2 would be the actual atom positions, the position vectors of the atom. So that's the convention, the notation that we will use here. That is number one. Second point we have to remember is that we are talking of electrons in a periodic potential. So therefore, whatever wave functions we write, they have to satisfy the block condition. So we must construct whatever way we form the linear combination of the atoms, atomic orbitals, they must satisfy block conditions if they are to represent electrons in a periodic potential. So the way one goes here is to first construct block functions that satisfy block conditions, and then form linear combinations of those block functions to construct electronic wave functions or the band wave functions. So here is the so I'll construct a block function. I'll explain these each one of these indices. See what we're doing here. Phi A is an atomic orbital on an atom which is sitting at a position Ri, where this Ri is some lattice vector plus this is called the basis within that particular sort of unit cell at R. So this is the position vector of the atom within a cell at the lattice point capital R. And phi A is one of the atomic orbitals on that atom. So I take that, then e to the I k dot Ri, and I sum over R. So this sum over R is sum over all the lattice vectors in my lattice. N is the number of unit cells I have in my physical crystal. So I take the 8th orbital, okay, on all atoms in my crystal. When I sum over this R, I get all the atoms sitting at corresponding positions, di at all the R's. I sum them over with this phase factor. So that gives me a block function corresponding to the wave vector R coming from the orbitals AI from atoms sitting at di in each sort of unit cell at each lattice point. So that's one of the block functions. Similarly, so as I go over A, all the different A's that I can have, and when I go over all the different DI's I have in each unit cell, I can construct other block functions. So I can construct several block functions like this. Okay, once I have formed these block functions, then I take a linear combination of these block functions to express my electronic wave functions, the band wave functions, or the molecular wave functions, whatever we are interested in. So now I'll focus on the discussion of solids. So we are talking of the band wave functions, psi nk. This is the same psi nk we encountered earlier, which are solutions of the Schrodinger equation for electrons within a periodic solid. N is the band index, K is the wave vector, and so on. So this is now expressed as a sum over this. So it's a two-step process. First, I construct the block function. Then I construct a linear combination of these block functions. So when I take linear combinations of block functions of same K for different A and I, I'll get the band wave function for that particular K. And I'll find different linear combinations for different band states. Okay, so now this sort of becomes a variational problem in the sense that I have to now find these A's, these coefficient, C's, these coefficient C's to sort of get my energy of the system or the wave function of the system. And what is the Hamiltonian with respect to which this has to be done? So this Hamiltonian is this, where this U, the potential that the electrons experience because of the ions, what do I write this? So this U is equal to this thing, which is a Coulomb attraction between an electron at R and all the ions sitting at these positions, where Zi is the atomic number of the corresponding atom. Okay, once we have set this up, and I would again sort of emphasize that please be very clear about the notations that are being used here. What is Ri? What is A, this index A? What this sum over R is. So you have to be absolutely clear about these things. And then this is a two-step process. You form block functions, and from the block functions, you form the bandwidth functions. Once you have formed the bandwidth functions, then you just put this in the eigenvalue equation. So that equation is simply this. And here, in place of this psi and k, I'll put this expansion. Sorry, there was a factor that oh no, this is okay. This part is fine. And then, okay. So after this, I'll write these chi i's in terms of these phi a's that I had written. So there I have this factor. 1 over root n over this has to be no, I'm missing things. Let me write this line once again. Sorry. Okay, so here I'm short of a board space. So let me see. So basically now after this, what you have to do is you're trying to find out the sort of matrix equation corresponding to these expansions. So basically what you do is, the general trick is to take a scalar product with some other block function for the same k. Okay. So you take the scalar product of this or this equivalently with some chi bj, where chi bj has a similar expansion. So let me write a prime here. This expansion means the atoms are actually sitting at locations. So chi rj is a location that is r prime plus dj.
Sir?
Yes?
Sir, in the top of the board, in the expression of psi and k, this summation is over a and over I, right?
Right.
Okay, sir.
For the same k, you sum over all chi ai's to construct your band function. Okay, so if you have written this much, I'll share these notes anyway. So if you have written this much and you have followed this much, and there's nothing new, no new physics happening here, it's just some algebra, and you have to just keep track of the indices and so on. So basically, then we'll take the scalar product with chi bj. So let me erase this. So on the left-hand side, you will have the factors of n and all will go away. So actually, this CNAI, the way I have expanded psi nk, CNAI will also have a k index here, because it depends which psi nk I'm expanding. For different k's, just as for different n's, these coefficients will be different. For different k's also, these coefficients will be different. So there'll be a k index here, which I missed in the earlier, what I wrote earlier. So that's the left-hand side. So notice here that in what is extra here is simply these factors, okay, these things. Otherwise, this is just the matrix element of the Hamiltonian that we got in the molecular case also, and this is just the overlap integrals of the atomic wave functions that we had earlier also. So what is extra is this K index, which comes in because of the periodic nature of the potential. So then you can, manipulate this, and eventually I'll just skip a couple of steps here, and you can write this equation as I'll define these terms. And simply now changing the indices, I'll make A the sort of free index. Now, what are these objects and how do we get here? H. Okay. Okay, so I'll give you a minute or so to sort of look at it, write it down, and then we'll slowly try to digest it. So how do we get this or this? See, this is the matrix element of the Hamiltonian between these two atomic orbitals, some phi b orbital at Rj and phi a orbital at the atom at Ri. This is something we had encountered earlier. So that is this object HABRIJ defined this way. So there is a Hamiltonian here. And this thing is sort of the Fourier transform of that. So when I take this object and do this transform, I get something which I call HAIBJ at K, at a particular K. So that is how from this I get this. And in the second term, this is epsilon nk. And then what I have done is I have this is just a simplification one does here, and the simplest tight binding Hamiltonian one writes. One just neglects these overlap integrals, as we did in case of the molecule also. So we'll just say this is delta AB, delta IJ, unless we have atoms happen to be the same, that is Ri equal to Rj, and the orbitals happen to be the same. Of course, if Ri equal to Rj, then you automatically get delta AB because atomic orbitals on the same atom are orthogonal. So that's how you get that. So that is the sort of final equation we get from this. So here in this term, I'll have diagonal matrix elements, I'll have off-diagonal matrix elements, and so on. So let us try to look at this a little closer. So what I would do is I'll take this HAB. So first let us look at the intra-atomic matrix elements. So when I say intra-atomic matrix element, basically we look at the same atom. So Ri is equal to Rj in this case. The same atom, the orbitals could be different. So A could be different from B. If I have more than one orbitals on the same atom in my basis, then A could be different from B, or A could be the same as B. So HAB Ri is what I'm looking at. So I'll write that. So I could have A equal to B. I could have, I'm missing the H once again. So there is an H here. I could have A equal to B or A not equal to B. And let me write the Hamiltonian once again. So this potential U that an electron experiences is due to all the atoms or all the nuclei that I have in my crystal. So this index I runs over all the atoms in my crystal. Okay, so then I can write H as, if I'm looking at the atom sitting at Ri, I will write H as, so if I take this part, the kinetic part, and this particular atom sitting at Ri, I take out that Coulomb potential. So then I can write that part simply as the atomic Hamiltonian for the ith atom, or the atom sitting at capital Ri. That's my H atomic I plus the full U of R minus bad indexing. Let me call this J.
Sir?
Yes. Yes, go ahead. Who is it, Aman? Aman, I cannot hear you.
Sir, there is a del square missing in the kinetic part of the Hamiltonian.
Oh yeah, the del square, that's missing. I'm sorry. Yeah, of course. Okay, so what I'm doing here is I'm taking out the atomic Hamiltonian part for the atom at capital Ri separately, and this is the remaining part. Okay. So this thing, because this is the atomic Hamiltonian, will simply give me epsilon A delta AB, right? Because if A is not, I mean, this just comes from, these phi A and phi B are eigenfunctions of this Hamiltonian, and they are orthonormal. So that is what I'll get from this. And then if we call that delta U, plus some term, which is let me call that delta U. Okay, that's that. So apart from the algebra, what we learned from this? What we learned from this is that if I neglected this term, then I'll simply have this. So even if I include more than one orbitals on my in my basis function, when they happen to be the same, that is for the diagonal terms of the Hamiltonian, I'll simply have the diagonal terms would simply be the corresponding atomic energies in those orbitals. However, if we include this term, there are additional contributions, and which come because of the neighboring atoms or all the other atoms in the crystal. Okay, so even in the on-site term, what we call on-site term, the diagonal matrix elements of the Hamiltonian, there are contributions from the neighboring atoms or distant atoms in the crystal. It's not a strictly local property of the atom we are considering. So this is a point that is quite often missed. I mean, my purpose of going through this entire sort of detailed algebra is to bring out this point and to point out that there is a chemical basis to the tight binding model, because often what physicists do is they are interested in perfectly crystalline solids. So you quickly go over to a second quantized representation of the tight binding Hamiltonian, where you have, I haven't yet talked about, but the off diagonal terms. And if you have only one type of atom in the crystal, all the diagonal matrix elements are the same. Is the constant, so you can even simply remove that, and you have this very simple tight binding Hamiltonian. But in actual cases, if you want to apply tight binding model to real materials, then you have to worry about this, okay? Because even diagonal matrix elements of the Hamiltonian depends on other atoms, not just the atom you are looking at. And I'll give you an exercise to sort of work out that has immediate consequences if you want to study, let's say, the edge atoms or the surface atoms of a finite crystal. Okay, so that's the intra-atomic matrix elements. Now you have interatomic matrix elements when Ri is not equal to Rj, and you'll simply have matrix elements in the Hamiltonian between some phi A at Ri and phi B at Rj and so on. And in the simplest situation, one truncates those terms, the off-diagonal matrix elements, to the nearest neighbors. There is no guarantee that if you are interested in a real material, that truncating it to a nearest neighbor would give you the meaningful physics that you were looking for. But as a model, that's a good starting point. So we'll just look at that situation. And yeah, I hope that will be enough for this course.
Sir?
Yes?
So in the rightmost part of the board, you have, what have you written? All atoms in the,
in the crystal. In the crystal.
Okay. Okay, okay. And sir, in the leftmost part of the board, if Hi atomic acts on phi b, that should give you Eb. Eb phi b.
We're talking of this?
Yes, sir.
Doesn't matter. You have a delta A beta. Okay.
Yeah, that is my point.
This can very well act on this as well. This is a Hermitian operator. So it doesn't make a difference whether you write epsilon A here or B here. So this matrix element of this between these two functions would give you this.
Yeah, yes, yes. Okay.
Okay. So now what we'll do is we'll see the application of this in one simple case. And other cases I'll ask you to work out. So I'll keep this line. Now let us take a simple case where I have one D chain. And I want to use this in order to get an expression for the energy. So I have one orbital per atom. So, there are no different A and B indices. Once I fix the atom, the orbital is automatically fixed. So I take one of these atoms, whatever, and I have some on-site term, which I just wrote, the intra-atomic orbital. And because A is equal to B, because there's only one orbital, so I'll get some constant energy. So which I can write it as a constant. I can just put it as 0 of my energy, doesn't matter. So let us ignore that term.
Sir?
Yes.
So please repeat last 30 seconds or so, because your voice got cut.
So we are trying to use the tight binding Hamiltonian that we discussed, the tight binding method, to the case of a linear 1D chain. And the target is to find out the band energy, this thing, for a linear 1D chain in which I have one orbital per atom. Because I have one orbital per atom, so in this Hamiltonian matrix elements that I had written earlier, R, H, A, B, R, I, R, I, A has to be equal to B because I only have one orbital per atom. So there is no on-site or intra-atomic off-diagonal terms. Intra-atomic here would mean diagonal terms because A has to be equal to B. There is only one orbital per atom. So basically, I'm saying what is then A, H, A, R, I, R, I. This will be some constant, some number for same for every atom, because I have an infinite chain of atoms, same atoms. So it is some number epsilon or epsilon 0 if you wish. So let us put that equal to 0. So I don't worry about that. That's a constant shift of energy. Doesn't tell me anything interesting. I have to worry about the off-diagonal terms here. And here I'll restrict myself to only nearest neighbor terms. So when I talk about H, A, I'm not writing the A, B index anymore because there are no different A, B indices. So I have H, R, I, R, J. So I restrict these terms only when Ri and Rj are nearest neighbors. So if I am sitting on this side, then I consider that the off-diagonal matrix element like this is non-zero only when I look at orbitals on this and this or this and that. So that's called the nearest neighbor tight binding model. I neglect here to here. So these things are neglected. So this will give me, so this is an integral, right? So phi minus Ri this is some integral, and it will be the same integral whichever pair of neighbors you take. So let us call that some number which is minus t. Okay. Right. So see if you work this out, I should. Okay, doesn't matter. Yeah, so then what I'll have is, so sitting on any atom, when I sum over Bj, so sitting on any atom Ai, when I sum over Bj, I'll only pick up two terms. One, so if this is my eighth atom, when I do this sum over Bj, I'll pick up only two terms, only when B is this one or that one. So in those two cases, and this integral has been written as minus t, so I'll pick up two terms, minus t. Then one of those terms will give me e to the I Ka, where A is the nearest neighbor distance. So basically this vector from here to here is minus A, and here to here is plus A. So I'll have these two terms. In 1D, that will be the condition that I have solutions for this C coefficient. So this will simply give me so that's the band energy of a 1D tight binding model with one orbital per atom, where you have truncated your hopping terms. So these are called hopping terms, once again, to the nearest neighbors. So this is called the nearest neighbor tight binding model in 1D. You can similarly work it out on a square lattice for 2D and so on, or a cubic lattice on 3D and so on. So if you have a square lattice in 2D, you will pick up two terms, cos kxa and plus cos kxy. So you just add another direction to it. So this already tells you a few things. It tells you what the band energy looks like. So I have a 1D chain with lattice constant A. So my Brillouin zone, the first Brillouin zone, goes from pi over A minus pi over A to pi over. And in this range, so this will go something like this. So as a function of k, so this is my k space. This is as a function of k, this is what the band would look like. And the maximum value would be twice t, and the minimum value would be minus 2t. So this difference is what is called the band width. The difference between the maximum and the minimum values that you get in a band is a band width. And here also, if you have one, now what we have considered so far is a linear chain and one orbital per atom. What we have not considered is, or not said, is that what is the number of valence electrons per atom. If you have one electron per atom on top of that, or let me write that here. Then half the states would be occupied, right? Because the number of k states within the Brillouin zone is equal to the number of unit cells in my crystal. This is something I stated earlier. So let me remind you, the number of k states in a Brillouin zone is equal to the number of unit cells you have in your crystal. So if you have n unit cells, there are n states in this. You can accommodate 2n electrons, but then you only have n electrons because there is only one electron per atom. So half the states will be occupied, half the states will be unoccupied. So you will have a metallic system. So therefore, one electron per atom, which is called the half-filled case. So in a half-filled case, in a tight binding model, you have a metallic system with exactly half-filled band. If you had 2 electrons per atom, it would give you an insulator. Of course, there is not much meaning of an insulator in the sense that in a model with one orbital per atom, you only get one band, but that band will be completely filled if you had 2 electrons per atom. Yeah, any questions at this point? Kaustav, is it clear to you?
Yeah, sir.
Okay, very good.
Sir, if we use 2 orbitals, will we
Yes.
get 2 bands?
You'll get 2 bands, yes.
So is it in general, I mean, that if we use n bands, n orbitals, we will get n bands?
Right. Okay, so as far as the tight binding model is concerned, I'll stop here, and the rest of the things I'll ask you to work out in an assignment. The other concept that I want to introduce now is, I'll come to that. So basically now here it seems like that, let us understand the conceptual difference between what we did earlier and what we are doing in the tight binding model. In earlier analysis, we were expanding this band wave function in terms of plane waves. Now, what we have done is we have taken localized orbitals on each atom and used those as the basis functions to expand the band states. It may seem like that's the only possible way of using localized wave functions to express the band states. Actually, turns out it's not quite true. In fact, I'll now introduce what are called one-year functions. Once you have constructed the band functions, you can then do a transformation of them and get localized functions. So it's a reverse process, sort of. In whichever way you do a calculation, get the band states of the electrons, and then do a transformation to get orbitals or functions that are localized on a particular atom. So let me introduce the sort of mathematical expression, which will make it clear to you. Sorry, this is a function of R. So this. So this would give you likely a wave function that is localized at the lattice site capital R. So basically you are doing sort of a transform of the band wave function psi and k. So for a particular band, you combine all the wave functions at different k's for that band. That is the sum over k with this phase factors. And that will give you some function which is localized around the lattice point capital R. And these functions, these WNs, these are called one-year functions. And you can do an inverse transform of the one-year functions to get back the band functions. But what I want to point out also is that these functions yeah, so these one-year functions they are orthonormal if the band wave functions psi nk and psi nk primed are orthonormal. So this follows from the condition. You can just plug this in, this expression in this and see it. Actually, there is a lot more to one-year functions than just this. But I'm not sure, at least at this point, I don't want to get into that. If we have time, then maybe later we'll get into an expansion and a discussion of that. But I just want to make a comment that sometimes once you have done a band structure calculation by using some method for real materials, then one forms these one-year functions, okay? And then these one-year functions are used as the basis functions for the tight binding model rather than the atomic functions. So that's a very sort of widely practiced procedure. So you do some realistic band structure calculation, maybe even including electron-electron interaction effects, get your band states, do a transform like this, get your one-year functions which are localized, and then use those localized functions to construct your tight binding model, which will presumably be more realistic. Another comment I want to make is that quite often in physics, this tight binding model is used as a model. So there are two approaches that one takes. There's a section of sort of people, depending on what questions they are interested in, they treat these terms T, for example, or the on-site energy in the tight binding model as just parameters. They don't really worry about their values. So you get qualitative answers if you take that approach, and maybe that is the kind of things they are interested in. But there could be other set of people who are interested in actual materials where the numbers are important. So they have to be sure what T is, what these epsilons are, and if there are other parameters. If you go beyond nearest neighbors, there could be a nearest neighbor hopping, then there could be more than one T's and so on. So they have to extract those values. They have to get numbers for those quantities in real systems. So sometimes these are done by fitting results of tight binding model to experimental results or to some other calculations. And yeah, so those values are extracted and then realistic quantitative models are built based on the tight binding model. So these are the two different sort of approaches that are taken towards the tight binding model that I wanted to mention. Any more questions?